Okay, so like we were saying, you just want to draw your compound, right? And it doesn't matter how you draw it, just as long as you're consistent, right? Which has been my main thing that I always say in this part of the class. Right, so fluorine, bromine, hydrogen, hydrogen. Okay. So an enantiomer of A, what's an enantiomer?
A non-superimposable mirror image.
Yep, so all you would do then is just draw the mirror image. Make sense?
Mm-hmm.
Right, and that's it. So now, what is, I'm pretty sure it's going to say diastereomer at the bottom here. What's a diastereomer?
Isn't it a non-mirror image and superimposable?
Yep, so now if I move this down here, right? So imagine this is it. All I would do is just switch one like that. So this would become HF like that.
Mm-hmm.
And for the other one, I would keep it the same as I originally drew it, FH, and then I would just switch the bottom one like that. Oh wait, no, that was right. Sorry, that was right as drawn. Does that make sense?
Yeah.
And that's the simplest way to do it. Just draw it the first time. Doesn't matter how you draw it, and then just flip things around. Are you guys all good? Need a moment to write this down.
Wait, for...
So here, I'm going to go back up to the top and I'm going to draw the original ones again up here. So for our original one, right, it doesn't matter how you do it again, just be consistent. So CH3, right? And then it was FBr, H. So for an enantiomer, you flip both of them, right? So H, F, Br. For the bottom one, you're going to flip, if you keep the top one the same, F, H, you flip the bottom one. So this becomes H, Br. And then if you do this one, you flip the top one, but you keep this the same.
Okay.
And then still the same CH2 up here on top, right, for all of them. And does that make sense though for how to do that?
Yeah.
Okay. All good? Ready for the next one?
Yeah.
I still need to send Mag a pizza.
You can send it on Thursday.
Okay. I'll send you a pizza if you tell me what dorm you're in. I will send you a pizza. I have no problems against doing that. This is awful.
Oh my gosh, we did those in class and I was confused.
Okay, so this is why I hate Fisher projections. So
she drew like a dead bug and was like,
yeah, she was
putting like feet on it, and I was like, okay.
So basically, this is what a Fisher projection is that, do you guys know why we do Fisher projections? Do you have any idea why we do them?
No.
We use this for sugar chemistry. This relates to things like for sucrose and glucose and stuff like that. So this is a biochemistry way that we do things. There's other reasons I won't get into because it's not important, but basically we relate this to sugar. And so it's very important that we draw this correctly when we do this. So it doesn't matter which side you start on and which side you make the top. Which side do you want to make the top? The COOH or the OH?
Oh.
Which way?
The OH, the top.
Okay, so we're going to say OH. If I turn on the writing tool. Okay, so we have to turn all of the carbons one by one by one. But this is an easier way for you to do this. This is basically, I think, what she was trying to say, or what she was saying. So basically, how many carbons do I have between my COOH and my OH?
5.
5. So I'm going to, I don't know why that keeps happening. I'm going to draw my OH, and I'm going to go 1, 2, 3, 4, 5, COOH. So 1, 2, 3, 4, 5. Okay, so my first carbon, my third carbon, and my fifth carbon, they alternate. The odd ones are going to stay the same. Wedge, OH, dash, H. 3 is still going to be dash, OH, wedge, H. And then 5 is still going to be dash, O, H. Like that. Does that make sense? And so now, when you do this, these are going to, your 2 and 4, your even ones are going to flip. Dash, OH, dash, OH, and wedge H, wedge H. Does that make sense for how you do that? So now if I'm looking at it like this, it's top down. So all your wedges will go to the right. All your dashes will go to the left. Does that make sense? Does she have an answer key for this?
Yes. Yeah.
Could you double check that to make sure? This is the one thing that I always feel just a little dicey on because I don't use Fisher projections anymore. It never arises.
I'm going to look.
Because no one uses Fisher projections. Right. Is it right?
It's right. Yeah.
I am the smartest. I am the smartest man alive. No, I'm not. If I was the smartest man alive, I would be somewhere in a chair, like I said, with a husky at my feet.
No, yeah, it's the same, except she just did COOH on the top, so it's just like flipped, but it's the same.
Yep.
So wait, why did we only flip 4 and 2?
Do you want the complicated reason or do you want the simple reason?
Simple.
Trust me. That is the simplest
Okay.
reason. But I
So
will show you. Okay, I'm going to show you real quick. I'm going to share a screen and I will highlight this. And when I say trust me, I'm not trying to sound like a dick. I'm just trying to make your life a little bit easier. All right.
Mm-hmm.
I promise you. I can be an ass, but not when I'm teaching unless someone's mean to me. But I try not to be an ass too much. So we're going to do a simple one. So we're going to do wedge A, wedge B, wedge C. Okay, so if I start at X, right? And I go up here, this is going to stay the same. This will still be a wedge A. Okay, but now remember how I want to make like that ring like this kind of thing where they're all pointing out? I have to rotate this bond like this. So I'm going to have to turn it 180 degrees. So this is pointing out to me. If I rotate my hand 180 degrees, which way is it now going?
Towards us.
It's, yep,
Or
away from us. Yep. So then this is going to be to here. So now this is going to be on a dash. However, I just rotated here. This is still the same, right? Well, hold on. I rotated. So now this is still the same. Get to that. There we go. I need a new computer. So this is still coming down, but when I rotated this like this, this is going dash down like this now, right? Because it was going this way. Now I just turned it down like that. But I need to rotate it so it's pointing up. So now when I rotate this bond like this, it's going down. I'm going to rotate it back up like that. It's now going to be X to here, to here, to here. So this is still wedge A. This is still dash B. But now this is back to being wedge C. And then this comes down to Y. So does that make sense that as I rotate, A doesn't rotate, right? 0 rotations, it's 180 degrees. Does that make sense? How many times did I rotate B, the bond to B? Once, twice, 3 times?
You rotated it once.
Yep, I rotated it once. Sorry, let me draw. I erase this. So I rotated 100. I rotated this 180 degrees, and then this got rotated 360 degrees, right? Because it got rotated when I rotated the first thing, and then I'm rotating it a second time. So if I rotated a second time, 360 degrees, I end up back in my original position. Does that make sense? So
yeah.
So if I'm like this, if I'm a wedge, 1 rotation, opposite, 2 rotations, back to normal. Another rotation, down. Another rotation, back to where I started. So if it's an odd number of rotations, I'm going to be going in the opposite direction. If it's an even number of rotations, I'll end up facing the same direction I started in.
Okay.
You don't sound happy with that answer.
It's just like, I don't know why the rotations, I don't know, they're just, Fisher projections kind of seem like unnecessary to me.
I already said that, but imagine these are my 2 substituents, right? And so now I rotate. So they both go like this, all right? So I rotated once. So now they're pointing in the opposite direction, okay? But now if I rotate this one again, it's going to be back in its original position.
Yeah, okay.
So this again falls into, I told you don't open this door because I told you you were not going to be happy with it. So the easiest way, and it's good to ask these questions. I'm not saying don't ever ask questions, but in this case, whenever you have some type of, it doesn't even matter how long this is, figure out what is at your top. If you make this the top and this is your bottom, doesn't matter which way you go, left to right, right to left, whatever. Count your carbons. 1, 2, 3, 4, 5, 6. All of your odd ones will be the same. Your wedges and dashes are going to be the same, whatever they currently are. All of your even ones are going to flip. So all the wedges will become dashes, all the dashes will become wedges. That is the easiest way to do that.
So what you said, all the even ones will flip and all the odd ones will stay the same. Okay.
And this is part of, I'm not trying to like dissuade you or anything, and I really hope I'm not coming off like an asshole, but it's just, there's no reason to understand it because no one's going to ever ask you to do those rotations, like actually demonstrate it. They're just going to ask you to take a drawing or take like a structure and then make the drawing of it. So if you just know the simple idea that the odd ones stay the same and your even ones flip, it makes your life a little bit easier.
Okay.
Again, I apologize if I'm coming off rude.
No, you're fine.
I feel that you're going to hit me the next time I'm on NAU's campus. I sense that voice.
I don't want. No, I would never.
Mag, defend me.
I will be here
Dead to me,
to
Max.
defend you.
Dead to me.
I'll come up and defend you.
What are you doing here, Dr. B? I'm waiting for one young woman to come up and fight another young woman for me. Because I truly am a coward. Okay, draw the most stable conformation on the provided chair except for D. Okay, so A, it wants us to do trans 1,3 isopropyl ethyl cyclohexane. So which of those is bigger?
The hexane,
The ethyl cyclohexane, right?
Yeah.
So we want that to be in the which conformation?
Equatorial.
Equatorial, right? So does it matter which way that ethyl cyclohexane is, if it's up or down right now?
No.
No.
It doesn't matter. It just matters its relative position to the one group. So which carbon do you want to make 3 out of the 6-membered ring there? Which carbon, Gwen, which one do you want to make 3? You're muted.
I'll do the furthest one to the right on the top.
Okay, so I'm going to just circle that to make sure that I'm going to put a dot here. This one?
Yeah.
Okay, so is my equatorial going up or is it going down here at this carbon?
Up.
It's going down.
Oh.
Because remember, the arrows, the lines going to the carbon are pointing which direction?
Oh.
That tells you the direction of the axial. Because if you notice this line of pointing the carbon's pointing up, this line's pointing up. So that tells you that the axial is pointing up.
Okay.
I know, just that surprising, right? So this is going to be equatorial down, right? And so this is going to be ethyl cyclohexane. So 1, 2, like that, all right? So now, 1 isopropyl. So do you want to count to my left or to my right, or does it matter? It doesn't matter, right? Just as long as you are consistent. So if this is 3, you are 2, you are 1. So since this is trans, does my isopropyl need to be pointing up or down?
It needs to be pointing up.
Yep, I think Gwen said up. She was muted.
Yeah, sorry, I didn't realize I was on mute.
No, that's fine. So this is going to be up isopropyl, and that's it. It doesn't.
Wait. Sorry.
No, go ahead.
So, you decided that one was gonna go down and the other one up because it's strands.
Yeah, and remember, what have I always said? What do I keep saying about these?
Consistency.
It doesn't matter which way you make something unless it tells you. You just have to be consistent.
Okay.
Could I have drawn that ethyl cyclohexane up?
Yeah.
You could have, right? It just, as long as you keep everything consistent with what you're given, it doesn't matter. So for the next one, right? Trans 1 tert-butyl 4 methyl cyclohexane, would they be pointing the same direction or opposite directions?
Opposite.
Yep. And it doesn't matter. Does it matter if the tert-butyl is going up or down?
No.
Nope. It's just whatever direction I give it, the methyl cyclohexane has to be pointing the other direction. So which one of these should go into the equatorial?
Methyl cyclohexane.
Yep, but what you're going to find out is, if you draw this, if I call you carbon 1, this is equatorial. This is going to be also equatorial. So they're both in the equatorial position. Does that make sense, or are you a little confused by that?
I think I'm a little confused.
What confuses you?
Because the other one we did, one was like axial and the other one was equatorial, and now they're both equatorial.
Are they on the same number of carbons?
No.
1, 3 versus 1, 4.
Oh, I get it.
So again,
Right.
if you're if you're right though, if it was 1, 3 again, one should be in the equatorial, right? But in this case, since they're trans 1, 4, both of them can always be in the equatorial.
Okay.
You sound angry, disappointed.
No, I was just confused.
That's okay. Just practice. And again, when you're drawing these, just pick a carbon and make it a number. Doesn't matter what. And just draw it. If worst comes to worst, draw it and say, I'm going to put you in the equatorial, or I'm going to put you in the axial. Try and draw it and see what happens. Okay? So,
Okay.
all right. Cis 1,2 tert butyl 2 methyl cyclohexane. So now, which of these, I think you said that the methyl cyclohexane should be in the equatorial. Okay, so
Yes.
Mags, which carbon do you want to make 1? I'm going to start circling carbons and tell me to stop when you want when you find one that you want me to make 1.
That one.
Okay. So we have cis tert butyl 2 methyl cyclohexane, right? So which direction do you want me to draw my tert butyl? Up or down?
Up.
Okay, so if this is up, right? Which carbon do you want me to make 2? To the left or to the right?
To the right.
Okay, so this one?
Yeah.
All right, so my methyl cyclohexane, should it be pointing up or down?
Up.
Up.
Up. But now this is going to be equatorial, right?
Yeah.
Oh. That's not methyl cyclohexane. That's just cyclohexane. I apologize. There you go. Are they cis?
Yes.
Are they both pointing up or both pointing down?
Both pointing up.
Okay. Are they on carbons next to each other? 1, 2.
Yeah.
Okay. Is the methyl cyclohexane in the equatorial position?
Yes.
Okay. Then is this drawn correctly?
Yeah.
Okay. So now it wants us to do a ring flip. So do you guys remember how to do ring flips? The carbon that's furthest to the right will always be the carbon that's furthest to the right. Right? So this is going to be my tert butyl now. Now this will still be pointing up, but now it's equatorial, correct?
Yeah.
And so when I went from 1 to 2, am I going clockwise or counterclockwise?
We're going to go counterclockwise.
Clockwise, because this is 1, this is 2, right? I'm going clockwise. So then this is going to be
sorry.
this is going to be my methyl cyclohexane here. Like that. Does that make sense? They're still pointing up, so they're both cis, right? They're cis to each other. They're on carbons 1 and 2 next to each other in the same order. And now, where one was equatorial, it's now axial. Where one was axial, the other is equatorial. Are you guys reaching your limit for chemistry nonsense for the evening? Everybody starts to tap out at some point. I've been doing chemistry since 8:45 this morning, so I'm always done with I've been doing chemistry since, well, a while, since you guys were in elementary school. I'm kind of done with chemistry.
You have your exams to grade, so.
No, we can keep going to finish this, but I was just checking to make sure that you guys are still doing okay. But the same thing that I know I harp on it all the time is just be consistent with all of this stuff. Okay, this is an easy one. So reactants and products, which goes on the left side?
Reactants.
Yep. What goes on the right side?
Products.
Okay. Do I have any transition states here?
No.
Yes.
Oof,
Anytime
okay.
you have a peak,
okay,
that is always a transition state. An intermediate is when you go to a peak and come down, but you don't go all the way to your products. So there are no intermediates here, right? So every reaction will always have reactants, products, and transition states. Does that make sense? If you had an intermediate, it would be like this: one hump, second hump, like that. So it would be between two humps, and neither the reactant or the product. That's what an intermediate is. This is what C would be, but you don't have one here, so all you have is A, B, and D. All good? Mm-hmm. Oh yeah, no region on diagram for these labels. That is C. There is no intermediate in this diagram here. Questions on that one?
Mm-mm.
How long is this test?
Too long.
It doesn't seem. I think there's only 11 questions.
Oof. Okay, well, let's do this one. We'll stop here after this question, and then on Thursday we will continue with this and answer more questions.
Okay.
And on Thursday I'll send Mag a pizza. Who do you want a pizza from? Papa John's, Domino's, someone nicer?
Your pie. It'll be a birthday pizza.
Aw.
Yes,
How
your
old are you
pie.
gonna be? 12, 13? I don't know how old kids are.
20.
20. Oof. I told the girl today that she was 12 and she got mad. She's 15, but really I can't tell the difference. She's also 4'10", so I mean she looks like a 12-year-old.
Some people really look like very young.
If you're younger than like a junior or senior, you kind of blend in.
Yeah.
I can only tell juniors and seniors because I can tell that they've been in college for 4 years. I can see it on their face. So real quick, I want you guys to figure out how many chiral carbons there are. You guys have an answer? You still working on it?
I said 5, but I'm really not good at finding chiral centers. So
okay, so the easiest thing is just to eliminate anything that's not a chiral center. So I'm going to say you're gone, right? So I want to include you and you're gone. You're gone. So I get that all out of my carbons, right? Get that out of the way. Any carbon that has 2 hydrogens, like this one here, gone. This one's gone. Because remember, if you have 2 of the same thing coming off a carbon, it's not a chiral carbon.
Okay.
So 1, 2, 3, 4, 5, 6. You're not counted, you're wrong. 7, 8, 9. You have 9 chiral centers in there.
Oh wow. Okay.
Was it seriously that easy?
Yeah.
You're joking.
Nope.
But I'm
like a delta gamma, it's that easy.
Oh god.
I'm confused because
Just kidding. The delta gammas are very nice, and I was a house tutor for many years for them. Nice house. Just a fun joke. This is being recorded.
I'm confused because like a carbon will be attached to like 2 carbons.
But remember, it's only if it's a plane of symmetry. So let's look at this one here. This is to a CH2Cl, right? So that's unique, correct?
Mm-hmm.
This goes to a carbon, that goes to an OH. So that's unique because none of the other 2 go there, right? This goes to an oxygen, this goes to an oxygen. Are they the same? So far. This then goes to a carbon with 1 hydrogen, that goes to an oxygen, that goes to a carbon. This goes to a carbon with a hydrogen, but it goes to a carbon Cl, goes to a carbon OH. There's a difference there. If you find any difference, that's automatically a stereocenter.
So we have to kind of look beyond those carbons to see what they're attached to.
Mm-hmm.
Okay.
Imagine, this is a thought exercise. Imagine you had a carbon and you had an OH and an H.
Mm-hmm.
To the right, you had 1 million carbons. To the left, you had 1,000,001 carbons. That 1 carbon difference, even though there's a million there, that additional 1 carbon makes them different. They're not the same.
Okay.
So if you find any difference down the line, then they are different attachments. Mags, are you okay with that? You look a little...
I don't get these at all.
Okay, well here,
Like,
we'll do a couple step by step. So the first thing you want to do is just consider carbons, right?
mm-hmm.
So we will start at each carbon. What is attached to that carbon?
2 hydrogens.
It's an OH, right?
Oh.
A hydrogen and a hydrogen and a carbon. Are 2 of those groups the same or different? Are they all different, or do I have repeats?
2 are the same.
Yep, so that means that it is not a chiral center. You need to have 4 different things.
Okay.
That eliminates that. Okay, what about this carbon? What's attached to that?
Oxygen, a carbon.
I have a hydrogen. I have a CH2OH. I have a single bonded O. I have a CHCl and the rest of this whole ring. Are those all different, or are they the same?
Different.
They're all different. So is that a chiral center? Yes or no?
Yeah.
Yeah.
Yep. So this is not a chiral center. This is a chiral center. Does that make sense how you have to go through and kind of do that? The easiest way you can do this is just go through and eliminate any carbon that is bonded to 2 hydrogens. So if you have a carbon like this in a chain that's not attached to anything, you can eliminate that. If you have any carbon that is at the end of a chain, a terminal carbon, like a CH3, you can eliminate those as well.
And double bonds, right?
Double bonds, triple bonds. Yep.
Okay.
Doble. Are you guys all good with that?
Yeah.
Yeah.
Okay. Figure out how many chiral carbons are in this one.
Oh God.
Say okay.
Yeah. CH3. H.
What was my favorite thing? So I taught advanced analytical at, as I pause this.